Everything you sense about the world is a convincing trick. Your feet are on solid ground, the clock ticks steadily forward, and the sky stretches overhead. This is the comfortable illusion of daily life, but physics tears that curtain down to reveal a backstage of pure strangeness, where space bends and time stretches like taffy. By the end of this journey, you will understand how the very fabric of reality operates, from the smallest quantum loops to the expansion of the cosmos. We will trace the story from philosophers gazing at the stars to the hunt for a theory of everything, confronting questions like why time only flows one way and if the universe is a hologram. What feels most solid to you about the world around us? Our deepest intuitions about reality are ancient. For millennia, human beings looked up and saw not a void but a ceiling. The sky was a solid, crystalline sphere, and the stars were fixed points of light upon it. This was the universe of Aristotle, a vision that would dominate Western thought for 2,000 years. In this cosmos, Earth sat motionless at the very center. Everything beneath the moon, our world of birth, decay, and change, was the terrestrial realm, imperfect and mutable. But the heavens above were a separate, perfect domain. The sun, moon, planets, and stars were made of a fifth element, ether, and they moved in flawless, eternal circles. Space, in this view, was not an empty container. It was a set of nested spheres, each with its own purpose and nature, with no such thing as a true vacuum. The idea of nothingness, of a void, was considered a logical impossibility. Time, within this ordered system, was not a straight line rushing from past to future. It was a wheel. Life was governed by cycles, the daily arc of the sun, the monthly phases of the moon, the annual turn of the seasons. History itself was thought to repeat in great ages. This cyclical time reflected the perceived perfection of the heavens. Since the celestial motions were eternal and repetitive, so too was the flow of events. There was no absolute beginning or end, just an endless, rhythmic return. Yet even in the ancient world, whispers of a radically different reality persisted. A century before Aristotle, philosophers like Democritus and Leucippus in Greece proposed a stunning idea. They suggested that everything, including the soul, was made of invisible, indivisible particles they called atoms. And for these atoms to move and combine, they argued, there must be empty space for them to move through. They called this emptiness the void. Here was a seed of the modern concept of space as a mere stage, independent of the actors upon it. But this atomic theory was a philosophical fringe, overshadowed by the powerful, intuitive appeal of Aristotle's cosmic architecture. The stage was set not for a discovery, but for a collision. The comfortable, finite, Earth-centered cosmos would eventually shatter, but first, it needed to be measured with impossible precision. The cosmos needed a new architect, and he arrived with a mind built for clockwork. It was Isaac Newton who took the stage, sweeping aside the celestial spheres and declaring a new, starkly elegant reality. For Newton, space was not a set of nested shells or a property of objects. It was absolute. Picture an infinite, immovable stage, a vast and featureless container that existed completely independent of anything within it. This absolute space was the same everywhere, from the heart of the sun to the depths of a void between galaxies. It was the fixed, eternal backdrop against which all motion could finally be measured. Time, in his system, underwent a similar transformation. No longer a wheel, it became an absolute river. This was time as a universal clock, ticking forward at a constant, unchanging rate everywhere in the universe. Whether you were here on Earth or on a planet orbiting a distant star, 1 second was 1 second. This absolute time flowed from the infinite past to the infinite future, utterly unaffected by the events that happened within it. Together, this framework of absolute space and absolute time created what we now call the clockwork universe. It was a vision of breathtaking predictability. If you could know the position and velocity of every particle in the cosmos at one moment, Newton's laws of motion and gravity would allow you to calculate their positions and velocities for all future moments. The universe became a giant, intricate machine whose every tick and tock could, in principle, be forecast. This is the foundation of classical physics, and its power is undeniable. Think of a great ship sailing across a perfectly calm, endless ocean. The ship moves, but the ocean itself does not. The water is the absolute space, providing a fixed reference. The journey of the ship from one point to another is measured against that static backdrop by the steady, unwavering passage of absolute time. This framework explained the fall of an apple and the orbit of the moon with the same simple mathematics. It gave humanity its first true predictive mastery over the physical world, from crafting accurate clocks to plotting the trajectories of cannonballs and planets. For over 2 centuries, this Newtonian arena felt like the final word on reality. It was clean, logical, and powerfully intuitive, but what if the stage itself was not fixed? What if the river of time could bend and slow? The next revolution would come from a clerk in a patent office who would dare to question the absoluteness of everything. The clockwork universe had a ghost in its machine. Newton's absolute space was a perfect, motionless stage, but by the late 19th century, physicists faced a baffling question. They had come to understand light as a wave, like ripples on a pond, or sound moving through air. But every wave needs something to wave in. Sound needs air, water waves need water. So what medium was light waving through as it traveled from the sun to the earth, across 93 million miles of apparent emptiness? The answer, they decided, was a substance they called the luminiferous ether. This ether was imagined as an invisible, frictionless, and strangely rigid material that filled all of absolute space. It was the hidden sea through which the planets swam and light propagated. It was the physical embodiment of Newton's stage, the thing that gave absolute space its substance. The ether had to have impossible properties, being both insubstantial enough to not slow the planets, yet stiff enough to transmit light waves at the staggering speed of 186,000 miles per second. It was a necessary phantom propping up the entire elegant structure of classical physics. 2 American scientists, Albert Michelson and Edward Morley, designed an experiment to finally catch this ghost. Their logic was brilliant. If the ether was a stationary sea-filling space, then Earth must be moving through it as it orbited the sun. Just as you feel a wind on your face when you ride a bicycle, there should be an ether wind blowing past the Earth. A beam of light traveling with this wind should go slightly faster than a beam traveling against it or across it. Michelson and Morley built an exquisitely sensitive device called an interferometer. It split a single beam of light, sending the 2 halves on perpendicular journeys before bouncing them back to recombine. If the ether wind existed, it would delay one beam relative to the other, creating a telltale interference pattern of light and dark bands when they reunited. They placed their device on a massive stone slab floating in a pool of mercury to eliminate vibrations, and they took measurements at different times of the day and year to account for Earth's changing direction through the supposed ether sea. The result was a profound silence. There was no shift, no interference pattern, no whisper of an ether wind. The experiment, repeated with ever greater precision, yielded a null result. Light traveled at exactly the same speed in every direction, regardless of the Earth's motion. It was as if you dropped 2 stones in a moving river, and the ripples from each spread outward in perfect circles, completely ignoring the current. The implications were catastrophic. The luminiferous ether, the fundamental substance of absolute space, did not seem to exist. Physics was left standing on the shore of a terrifying and exciting abyss. The very stage upon which the cosmic drama was performed had vanished. If there was no ether, what was light waving in? And if the speed of light was constant for all observers, how could the absolute, universal time of Newton possibly survive? The null result was not just a failed experiment, it was a direct challenge to reality itself, a crisis that demanded a genius willing to question not just the answers, but the very questions being asked. Into this crisis of the missing ether stepped a 26-year-old patent clerk in Bern, Switzerland. Albert Einstein was not trying to salvage the old stage. He decided to build an entirely new one from the ground up. In 1905, he published his theory of special relativity, a set of ideas so radical they did not just solve the ether problem, they erased the need for it entirely. Einstein started with two deceptively simple postulates or foundational rules. First, the laws of physics are exactly the same for all observers moving at a constant speed in a straight line. Whether you are sitting perfectly still in a room or cruising smoothly on a high-speed train, the same physical rules apply. There is no privileged frame of reference, no absolute state of rest. Newton's unmoving stage was gone. His second postulate was the bombshell. The speed of light in a vacuum is constant for all observers, regardless of their own motion or the motion of the light source. This was the direct answer to Michelson and Morley's null result. Light does not need a medium to wave in because it is not behaving like a normal wave in a substance. Its speed is a fundamental feature of the universe itself, a cosmic speed limit written into the fabric of reality. Think of it this way. If you are standing still and throw a baseball forward at 60 miles per hour, and I run past you at 20 miles per hour and throw an identical baseball forward, I will measure my baseball leaving my hand at 60 miles per hour. But you will see my baseball moving at 80 miles per hour because you add my running speed to the throw. Speed is relative, but if instead of a baseball I shine a flashlight, something utterly bizarre happens. I measure the light beam racing away from me at 186,000 miles per second. You, standing still, also measure that exact same beam moving at 186,000 miles per second. You do not add my running speed. The speed of light is absolute. For this to be true, for the laws of physics to hold and for light's speed to remain unwavering for everyone, something else had to give. Einstein realized that the things we thought were absolute, space and time themselves, were not. They are flexible, malleable, and deeply interconnected. To keep the speed of light constant, space must contract and time must dilate for a moving observer. This single insight shatters our most basic intuition about a shared, universal present. If you and I are moving relative to each other, we will not agree on whether two events happen at the same time. Simultaneity becomes relative. The river of time, which Newton saw as flowing at the same rate for all, is now a network of tributaries, each flowing at its own pace depending on motion. The comfortable, separate arenas of space and time were gone forever, fused into a single, dynamic entity we now call spacetime. Einstein's new arena of spacetime came with a rule so strange it feels like a violation of common sense. There is no universal now. The moment you are experiencing as the present is not the same moment someone else, moving relative to you, is experiencing. To see how this works, we must perform a simple thought experiment. Picture a long, straight train platform on a stormy evening. You are standing exactly at its midpoint, perfectly still. Far off to your right and to your left, at equal distances down the tracks, two powerful lightning bolts strike the ground at the exact same instant. Because you are precisely in the middle, the light from each bolt travels the same distance to reach your eyes. You see both flashes at the same moment. For you, the two strikes are unquestionably simultaneous events. They share a single, definitive moment in time. Now, imagine a very long train is speeding past the platform from right to left at a significant fraction of light speed. A passenger is sitting at the exact center of one of its carriages, looking out the window. At the precise moment this passenger's position aligns with yours on the platform, the same two lightning bolts strike. From the passenger's perspective, however, the story is completely different. The train is moving toward the light coming from the bolt on the left and racing away from the light coming from the bolt on the right. This motion means the passenger meets the light from the left-hand bolt sooner. Its flash has a shorter distance to travel to reach the passenger's forward rushing eyes. The light from the right-hand bolt, meanwhile, must chase after the receding train, taking longer to catch up. The passenger sees the left flash first, then the right flash later. For the person on the train, the two strikes did not happen at the same time. The left bolt struck first, and the right bolt struck some tiny fraction of a second afterward. This is not an illusion of perception. It is not a trick of the light. In the fabric of space-time, the very ordering of those two events is different for the two observers. There is no cosmic referee to say who is right because both are right within their own frame of reference. The concept of now is not a line drawn across the universe. It is more like a personal angle, a slice through space-time that depends entirely on how you are moving. This single idea dismantles Newton's absolute timeline. If two people cannot agree on whether two events happened at the same time, then there can be no single master clock for the cosmos. Your past, present, and future are not the same as mine if we are in relative motion. Time itself is woven into your personal journey through space. This relativity of simultaneity is the foundation for all the other strange effects, like time dilation and length contraction. It means the universe has no center stage, no privileged viewpoint. Every observer carries their own valid version of reality, their own unique present moment. The solid, shared world of our intuition dissolves into a tapestry of perspectives, where the only true constant is the speed of light, tirelessly connecting every disparate now into a coherent, if deeply mysterious, whole. This relativity of simultaneity leads to a consequence that feels like pure science fiction. Time itself does not flow at a single, universal rate. A clock in motion ticks slower than an identical clock at rest. This is not a mechanical failure or an illusion. It is a fundamental property of space-time, a direct result of the unwavering speed of light. We can understand why with a simple but powerful thought experiment called the light clock. Imagine a clock made from two perfect mirrors facing each other, with a single particle of light, a photon, bouncing vertically between them. Each round trip up and down is one tick of this clock. It is a perfect, immutable timekeeper. Now place this clock on a spaceship moving at an incredible speed to the right and watch it from a stationary platform. From your stationary viewpoint, you see the photon's path. It is still bouncing between the mirrors, but because the spaceship is moving horizontally at high speed, the photon must now travel on a diagonal path. It goes up and to the right, then down and to the right, tracing a long, zigzagging route. This diagonal path is longer than the simple vertical path you would see if the clock were sitting next to you. And here is the unbreakable rule. The speed of light is constant. That photon must always travel at exactly 186,000 miles per second, no matter what. Since it has a longer distance to cover in the moving clock from your perspective, the only way for it to still go at light speed is for more time to pass between ticks. From your stationary frame, the moving clock ticks slower. Time on the speeding spaceship is dilated, stretched thin. This effect is minuscule at everyday speeds, which is why we never notice it. But as you approach the speed of light, time dilation becomes dramatic. For an astronaut traveling at 99.9% of light speed to a distant star and back, only a few years might pass on their ship. When they return home, centuries could have elapsed on Earth. The evidence for this is not just theoretical, it is measured daily in our atmosphere. Cosmic rays from space constantly strike the upper air, creating short-lived particles called muons. These muons are unstable, decaying into other particles in just 2.2 millionths of a second. Even traveling at nearly the speed of light, they should decay long before reaching the ground. Yet we detect them in abundance at Earth's surface. From our perspective on the ground, their incredible speed means their internal clocks are running slow. The 2.2 microsecond lifetime is stretched out, giving them enough dilated time to complete the journey to the surface. From the muon's own perspective, it is not time that is dilated but space. The distance to the ground is contracted, allowing it to arrive before it decays. Both perspectives are valid, two sides of the same relativistic coin. The most precise human confirmation came in 1971. Scientists flew state-of-the-art atomic clocks on commercial jets around the world, comparing them to identical clocks left on the ground. After the journeys, the flying clocks were found to be ever so slightly behind the stationary ones, exactly as Einstein's equations predicted. The difference was measured in billionths of a second, but it was real. Time itself had passed at a different rate at 35,000 feet. This is the reality we inhabit. Time is not a universal drumbeat. It is a personal rhythm, a tempo set by your journey through the intertwined fabric of space and time. But if motion can warp time, what happens when gravity enters the equation? The slowing of time has a perfect, inseparable twin. Just as moving clocks tick slower, moving objects physically shrink in the direction they are traveling. This is length contraction, the other side of the relativistic coin. If you could watch a race car scream past you at close to light speed, it would not just look blurry. It would appear dramatically flattened, as if pressed into a pancake from front to back. Its length from its grille to its spoiler would be contracted. Yet, from the driver's perspective inside the car, nothing is amiss. The steering wheel is a normal distance away, the pedals feel right underfoot. Their own ruler, their own sense of space is perfectly normal. The contraction is not a mechanical compression or an illusion. It is a real feature of how spacetime reconciles the constant speed of light for all observers. Let us revisit our light clock on the moving spaceship. From the stationary observer's view, time dilated because the light took a longer diagonal path. But from the astronaut's perspective inside the ship, the light is simply bouncing straight up and down. For them, the clock ticks normally. So how do they explain the fact that the outside observer measured a slower tick? The only way the math works is if the astronaut measures the distance between those mirrors as being shorter. Their entire ship and the space it moves through is contracted along its direction of motion. This is why the muon reaches the ground. From our Earth-bound view, its time slowed down. From the muon's view, the height of the atmosphere was not a fixed distance. It was a contracted, shorter path it could traverse in its brief lifetime. Length contraction ensures the laws of physics remain consistent for everyone. If you try to measure the speed of an object, you divide the distance it traveled by the time it took. For the speed of light to come out the same constant number for all observers, if the time measurement changes, the distance measurement must change in perfect concert. One cannot happen without the other. Space and time are in a constant, intimate dance, each adjusting to preserve the cosmic speed limit. This twin nature of time dilation and length contraction shatters the last remnants of Newton's rigid arena. There is no absolute length, just as there is no absolute time. A meter stick is not an immutable object. Its length depends on who is measuring it and how they are moving relative to it. The very fabric of space is pliable, responsive to motion. This means the universe you perceive is not a fixed, objective sculpture. It is a dynamic impression, a portrait painted by the interaction of your own motion with the immutable speed of light. The stage itself is elastic, but if motion can warp space and time, what could the far greater force of gravity do to this new, flexible fabric of reality? Motion and gravity were warping the stage, but the stage itself remained undefined. It was Einstein's former mathematics professor, Hermann Minkowski, who gave this new reality its breathtaking form. In 1908, he made a declaration that would reshape physics. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, he proclaimed, and only a kind of union of the two will preserve an independent reality. He had given the fusion of space and time a name and a geometry, spacetime. This was not just a combination of 3 dimensions of space and 1 of time. It was a single, seamless, 4-dimensional continuum. Think of it as a fresh loaf of bread. The entire loaf is the whole of spacetime, containing all events that have ever happened or ever will. Now slice that loaf. Each individual slice represents the entire universe frozen at one single, fleeting instant, a moment of now. As you move through the loaf from one end to the other, you are moving from the past to the future, viewing a succession of these universal snapshots. In this block universe, every event from the birth of a star to the fall of a leaf has a fixed location. Your entire life, from beginning to end, exists as a permanent shape within this 4-dimensional block. This is where the idea of a world line becomes essential. An object at rest in space is still moving relentlessly through time. In the space-time loaf, it traces a straight, vertical line from the slice of its birth to the slice of its end. Now, if that object starts to move through space, say, a planet orbiting a star, its path through the block is no longer a straight vertical line. It becomes a spiral, corkscrewing through the successive slices of time as it circles through space. That spiral is its world line, the unique signature of its entire existence through the 4-dimensional continuum. Even a seemingly chaotic path, like a fly buzzing around a room, has a precise, tangled world line threading through the loaf. Nothing is lost. Every twist and turn is forever etched into the fabric. This geometric view of spacetime was the crucial pivot. Physics was no longer just about objects moving through space over time, pushed by mysterious forces. It became the study of the shape of spacetime itself. The stage was no longer a passive backdrop. It was an active, dynamic participant, and its geometry would dictate everything that happened upon it. Minkowski's 4-dimensional arena provided the perfect language for Einstein's next, even greater leap. If the stage could be warped by motion, what would happen if its very substance, its geometry, was curved by the presence of mass and energy? The straight world lines of special relativity were about to bend into orbits, revealing gravity not as a force, but as the contour of the cosmos. The straight world lines of Minkowski's spacetime were about to encounter a monumental curve. For a decade after his theory of special relativity, Albert Einstein wrestled with a single, profound limitation. It described a universe of constant motion, but it could not account for acceleration, and most critically, it had nothing to say about gravity, the most familiar force of all. Newton had described gravity's effect with mathematical precision, but its mechanism remained a haunting mystery. What was this invisible pull that acted instantly across the emptiness of space? Einstein's breakthrough was to realize that the problem was not with gravity, but with our understanding of space and time. His monumental theory of general relativity, published in 1915, proposed a truth so elegant it redefined reality. Mass and energy do not exert a force across spacetime. They shape spacetime itself. Picture a taut, flat trampoline. This is empty spacetime, the smooth, 4-dimensional fabric of the universe. Now place a heavy bowling ball in the center. The trampoline sags, creating a deep, smooth depression around the ball. This is not just a metaphor, it is a direct analogy for how mass warps the geometry of the continuum. The Sun, a massive object in our cosmic neighborhood, creates a similar curvature in the fabric of spacetime around it. Now, roll a marble across this warped trampoline. You will see it not travel in a straight line. Instead, it will curve inward, spiraling toward the bowling ball. From a bird's eye view, it looks as if the marble is being pulled by an invisible force toward the heavy object. But there is no pull. The marble is simply following the straightest possible path through the curved landscape. It is moving along a geodesic, the equivalent of a straight line on a bent surface. This is the heart of general relativity. Gravity is not a force, it is the geometry of spacetime. The Earth orbits the Sun not because the Sun pulls on it, but because it is following a geodesic, a free-fall path through the curved spacetime created by the Sun's mass. We feel weight standing on Earth not because the planet is pulling us down, but because the planet's mass curves spacetime around it, and the ground is pushing us up, preventing us from following our natural geodesic path into the center. We are constantly being accelerated upward, away from our inertial path, and that sensation is gravity. This geometric view made a bold prediction. If spacetime is curved, then even massless light, which always travels the straightest path, must bend as it passes through a gravitational field. During a total solar eclipse in 1919, Sir Arthur Eddington led an expedition to measure the apparent positions of stars whose light grazed the Sun. The results confirmed Einstein's prediction. Starlight was deflected by the Sun's warped spacetime, proving that the very stage of the universe was malleable. Time, too, is curved by gravity. A clock at sea level, deeper in Earth's gravitational well, ticks slower than an identical clock on a mountaintop. This gravitational time dilation is not a theoretical curiosity. The global positioning system must account for it, or its navigation would fail within minutes. The satellites in orbit experience time flowing faster than receivers on the ground, and their clocks must be constantly adjusted for the theory of general relativity to keep us on the right path. Einstein had revealed a universe where matter tells spacetime how to curve, and curved spacetime tells matter how to move. But if the fabric can be warped, could it also ripple? Could gravity itself travel in waves? Einstein's curved spacetime was not a silent sculpture. It had a voice, and it spoke in light and time. The first great test came from a simple yet profound prediction. If mass curves the fabric of spacetime, then even a beam of light, traveling the straightest possible path through that curved geometry, must bend. It was a prediction that could shatter Newton's conception of gravity or elevate Einstein's to a new law of nature. The perfect laboratory was our own solar system. Einstein calculated that starlight passing close to the Sun should be deflected by a tiny but measurable angle. The problem was seeing stars next to the blinding solar disk. The solution was a cosmic coincidence, a total solar eclipse. In May of 1919, two expeditions led by Sir Arthur Eddington traveled to opposite sides of the Atlantic, to Sobral in Brazil and the island of Principe off Africa. Their mission was to photograph the stars in the darkened sky around the eclipsed Sun and compare their positions to photographs of the same star field taken months earlier when the Sun was elsewhere. If Einstein was right, the stars near the Sun would appear to have shifted slightly outward, their light nudged by the Sun's gravitational well. After months of painstaking analysis, Eddington announced the results. The measured deflection matched Einstein's prediction almost exactly. Light, the universe's fastest traveler, was not immune to gravity. It was following the contours of warped spacetime. The news made Einstein an international celebrity overnight, and it provided the first spectacular proof that space and time were not a fixed stage, but a dynamic, malleable fabric. This effect, called gravitational lensing, is now a fundamental tool of astronomy, allowing us to see galaxies hidden behind massive clusters, their light bent and magnified by the foreground curvature. But the warping of spacetime does more than bend light's path. It also stretches time itself. A second, equally strange prediction of general relativity is gravitational time dilation. The deeper you are in a gravitational well, the closer you are to a massive object, the slower time passes relative to a location farther away. Imagine two identical, perfectly synchronized clocks. Place one at sea level and carry the other to the top of a tall mountain. The clock on the mountain, experiencing slightly weaker gravity, will tick ever so slightly faster. Over years, it will gain a tiny fraction of a second compared to its twin at sea level. This is not a mechanical error. Time itself is flowing at a different rate. The most precise everyday proof of this is in your pocket or your car. The global positioning system is a constellation of satellites, each carrying an atomic clock of incredible accuracy. These satellites orbit about 12,500 miles above Earth, in a much weaker gravitational field than we experience on the surface. According to general relativity, the satellite clock should run faster by about 45 millionths of a second per day. If the system's computers did not correct for this, the navigation errors would accumulate at a rate of about 6 miles per day, rendering the system useless in a matter of minutes. Engineers must also account for the slower time dilation caused by the satellite's orbital speed, a relic of special relativity. The combined correction is a direct, continuous application of Einstein's theories, making your map app work. These are not abstract mathematical curiosities. They are measurable engineering-level realities. Starlight bends, clocks disagree. The universe is constantly proving that space and time are not a passive container, but an active, interactive participant in the drama of physics. If the fabric can be bent and stretched by mass, then what happens when that mass moves violently? Could space-time itself ripple, sending waves across the cosmos? The ultimate consequence of warped space-time is a tear in the fabric of reality itself. When a massive star collapses under its own gravity, it can create a region of space-time so profoundly curved that nothing, not even light, can escape its pull. This is a black hole, the point where Einstein's elegant geometry breaks down. The boundary of this point of no return is called the event horizon. It is not a physical surface, but a mathematical threshold, a one-way membrane in space-time. Once you cross it, every possible path you can take, every future world line, leads inexorably inward toward the center. There is no turning back, no force in the universe powerful enough to reverse that final descent. For an object falling toward a black hole, the experience would be both terrifying and strange long before reaching the horizon. The gravitational pull on your feet would be vastly stronger than the pull on your head if you were falling feet first. This difference in force, the tidal gravity, would stretch you into a long, thin strand of atoms in a process physicists grimly call spaghettification. But the true strangeness is in time. Imagine watching a friend, brave or foolish, fall toward a black hole as you remain at a safe distance. As they approach the event horizon, you would see their clock slow down relative to yours, an effect of extreme gravitational time dilation. Their movements would appear to slow to a crawl, their light reddening and dimming. From your perspective, they would never quite cross the horizon. They would fade, frozen in time, as the last photons they emit struggle to climb out of the gravitational well. For your friend, however, their own clock ticks normally. They would cross the event horizon in finite time, passing a point of no return with no dramatic sensation, just the inexorable pull toward the center. And at that center lies the true mystery, the singularity. Our equations tell us that all the collapsed mass is crushed into a point of infinite density, where the curvature of spacetime becomes infinite. Here, the smooth fabric described by general relativity develops a tear. The laws of physics as we know them cease to function. Space and time as meaningful concepts simply end. The singularity is a frontier, a glaring sign that our understanding is incomplete, that a deeper theory must take over where Einstein's masterpiece leaves off. Black holes are not just cosmic vacuum cleaners. They are the most extreme laboratories in the universe, places where space-time is tied into a knot so tight that it challenges our very definitions of reality. They force us to ask what lies beyond the end of space and time. Black holes curve spacetime into a bottomless pit, but on the grandest stage, the fabric of the cosmos is performing a very different act. In the 1920s, astronomer Edwin Hubble made an observation that would redefine our place in the universe. By analyzing the light from distant galaxies, he found a startling pattern. The light from nearly every galaxy was shifted toward the red end of the spectrum. This redshift was not a curious color change. It was a cosmic Doppler effect, the same phenomenon that makes a siren's pitch drop as it speeds away from you. The galaxies were all receding, moving away from us, and the farther away a galaxy was, the faster it appeared to be fleeing. This was the revolutionary Hubble law. The entire universe was not static, it was expanding. The immediate intuitive picture is of galaxies like shrapnel from a colossal explosion, hurtling outward through a pre-existing empty space. But general relativity paints a far more profound picture. The galaxies are not simply sailing through space, the very fabric of spacetime between them is stretching. Think of the surface of a balloon as it is being inflated. Draw dots on the balloon to represent galaxies. As you blow air in, every dot moves away from every other dot. No dot is the center. The space on the surface of the balloon itself is expanding, carrying the dots apart. This is the raisin bread analogy. Imagine a loaf of unbaked raisin bread dough. Each raisin is a galaxy. As the dough bakes and rises, it expands. Every raisin sees all the other raisins moving away. A raisin near the edge does not see itself as the center. From its perspective, all other raisins are receding, and the ones farther away appear to move faster because there is more expanding dough between them. This is our universe. We are not at the center of an explosion. We are on a raisin, watching all other raisins drift away as the cosmic loaf itself expands. If we can run this movie of the expanding universe backward in our minds, we are led to an inevitable and staggering conclusion. In the past, all those raisins, all that matter and energy must have been closer together. Further and further back, the universe was denser, hotter, and more compact. Rewind the tape all the way, and you reach a state of unimaginable density and temperature, a singularity of not just matter but of space-time itself. This is the Big Bang, the moment when the expansion of the universe began. It was not an explosion in space. It was the rapid expansion of space and time from a primordial state. In that first searing fraction of a second, space-time itself evolved, cooling and stretching, allowing energy to condense into the first particles, then atoms, and eventually the galaxies we see today. The echo of that initial expansion is still with us, a faint microwave glow that fills the entire sky. The cosmic microwave background, the afterglow of the Big Bang. So the fabric Einstein described is not merely curved by mass. On the largest scales, it is dynamic, growing, carrying the history of everything within its stretching threads. But if space-time can expand from a singular beginning, what does that mean for its ultimate fate, and for the very nature of nothingness from which it emerged? Our universe has a beginning, and that beginning holds the key to a mystery unfolding right now. The laws of physics, from gravity to electromagnetism, are almost perfectly symmetrical in time. If you filmed two electrons repelling each other and ran the film backward, it would look just as plausible. The equations work perfectly in reverse. Yet our experience of reality is utterly one way. We remember yesterday but not tomorrow. We see an ice cube melt in a glass, but we never see the puddle of water spontaneously reassemble into a cube. This is the arrow of time, and its direction is etched into the cosmos from the very first moment. The most fundamental arrow is the thermodynamic arrow, governed by a concept called entropy. In simple terms, entropy is a measure of disorder or randomness in a system. The second law of thermodynamics states that in any closed system, the total entropy always increases over time. Things tend to move from order to disorder. Think of a sandcastle on a beach. Left to the wind and waves, it will slowly erode into a shapeless mound of sand. That is entropy increasing. It is incredibly unlikely for the random motions of air and water to suddenly sculpt that mound back into a detailed castle. It is not impossible according to physics, but it is so staggeringly improbable that we will never witness it. This is why we have a past and a future. We remember the ordered state, the intact castle, the whole cup, the unmelted ice, because those are low entropy states. The future is the higher entropy state, the scattered sand, the shattered pieces, the warm water. Our brains, which are themselves physical systems obeying these laws, record the progression from order to disorder. That record is what we call memory. So why does entropy always increase? The answer lies in the starting conditions of our entire universe. The Big Bang was a state of extraordinarily low entropy. It was not a disordered explosion of matter flying into empty space. It was an incredibly hot, dense, and smooth state. Smoothness is a form of order. From that singular point of low entropy, the universe had only one way to go, toward higher entropy, greater disorder. As space expanded and cooled, that initial order began to unravel in a specific way, creating galaxies, stars, planets, and eventually the conditions for life. We are riding that wave of increasing entropy. The reason you see time flowing forward, the reason you can tell a story about your life, is because you are a product of that cosmic initial condition. Your very existence is a testament to the universe starting in a special, ordered state. Without that low entropy beginning, there would be no consistent arrow of time. Past and future would be indistinguishable, and consciousness as we know it might be impossible. So every time you see steam rise from your coffee and dissipate, or leaves scatter in the autumn wind, you are witnessing a local expression of the universe's deepest origin story. The arrow of time points from a unique past toward a probable future, and we are carried along its relentless one-way flight. Yet this elegant, continuous fabric of spacetime faces a rebellion from within. While general relativity masterfully describes the cosmos on its grandest scales, a completely different set of rules governs the universe at its smallest. This is the domain of quantum mechanics, and its portrait of reality is so bizarre it seems to unravel the very stage Einstein so carefully constructed. Here, in the realm of atoms and particles, certainty dissolves into probability. An electron does not orbit a nucleus like a tiny planet. Instead, it exists as a cloud of possible locations, a shimmering haze of maybe spread throughout space. It only settles into a definite position at the moment you measure it. Until that observation, it is everywhere and nowhere at once, a ghostly superposition of all its potential states. This is not a limitation of our instruments. It is a fundamental feature of reality at the quantum level. The universe at its foundation is not made of tiny billiard balls. It is built from fuzzy probabilities and potentialities. This inherent fuzziness is captured by Werner Heisenberg's uncertainty principle, one of the most profound ideas in all of science. It states that there are intrinsic limits to what we can know about a particle. Specifically, you cannot simultaneously know both its exact position and its exact momentum, which is its mass times velocity. The more precisely you pin down where a particle is, the less you can know about how fast it is moving, and vice versa. It is not that our tools are clumsy. The universe itself refuses to grant that knowledge. Think of trying to see a speck of dust in a pitch-black room using only a flashlight. To locate it, you shine a tight, precise beam. You now know exactly where it is, but in that instant you have no idea which way it was moving. To see its motion, you would need to use a wider, softer light, but then you would lose the precise knowledge of its position. In the quantum world, the act of measurement itself disturbs the system in an unavoidable way. This principle extends beyond position and momentum. There is a similar uncertainty between energy and time, meaning that on extremely short timescales, vast amounts of energy can spontaneously borrow into existence from nothing, as long as they vanish again almost instantly. These are not mere mathematical quirks. They are the operating system of the microscopic world, and they create a monumental problem. Einstein's general relativity describes spacetime as a smooth, classical fabric, like a perfectly woven silk sheet. But quantum mechanics insists that at the very smallest scales, near the Planck length, this fabric must be seething with violent, unpredictable fluctuations. Virtual particles pop in and out of existence, warping geometry in random, chaotic ways. The smooth sheet should look more like a frenzied quantum foam, a bubbling sea of probabilities where the concepts of here and now lose all meaning. This is the great schism at the heart of modern physics. We have two breathtakingly successful theories. One, general relativity, explains the force of gravity and the large-scale structure of the cosmos. The other, quantum mechanics, explains the other three fundamental forces and the behavior of every particle in existence. Yet they are fundamentally incompatible, describing the universe in mutually exclusive languages. For decades, physicists have searched for a theory that can marry these two visions, a single framework that can describe the quantum flutter of gravity itself. This quest for a theory of quantum gravity is the greatest unsolved puzzle in fundamental physics, and its solution promises to reveal what spacetime truly is, not just on our human scale, but in the furious heart of a black hole and at the very first instant of the Big Bang. The smooth sheet of spacetime dissolves into a frenzied sea at its very foundations. This is the quantum vacuum, and it is anything but empty. What we perceive as a void, a perfect stillness between the stars, is in reality a seething, bubbling cauldron of activity. According to the rules of quantum mechanics and the uncertainty principle, empty space is not a placid lake. It is a storm. On unimaginably short timescales, pairs of virtual particles and their antiparticle counterparts spontaneously blink into existence. One moment there is nothing, and the next a particle and an antiparticle have emerged from the vacuum itself. They are called virtual because they are fleeting, ephemeral phantoms. They do not last long enough for us to detect them directly. They borrow a tiny amount of energy from the vacuum, and by the strict accounting of quantum physics, they must repay that debt almost instantly. The particle and antiparticle annihilate each other, vanishing back into the nothingness from which they came. This is not a theoretical fantasy. We know it happens because it leaves a fingerprint on the real world. In a perfect vacuum, two uncharged metal plates placed incredibly close together will experience a faint, measurable force pushing them together. This is the Casimir effect. Why? Because the space between the plates is so narrow that only virtual particles with certain wavelengths can pop into existence there. The wider space outside the plates allows for a greater variety of these quantum fluctuations. The pressure from the more active vacuum outside pushes the plates together. It is a ghostly pressure from particles that are not really there, proving that empty space is alive with transient creation and destruction. But what does this quantum frenzy do to the stage itself, to the fabric of spacetime? If energy and mass are equivalent, as Einstein showed, and these virtual particles represent fleeting bursts of energy, then they must also warp spacetime. At the scale of an atom, this effect is negligible, but if we zoom in to the smallest possible scale, a distance called the Planck length, the geometry of reality should become chaotic. The hypothesis is that spacetime at this fundamental level ceases to be smooth. It becomes a turbulent, frothing foam. Picture the surface of a carbonated drink under a microscope. What looks like a flat, continuous liquid is actually a churning mass of bubbles constantly forming, merging, and popping. Quantum foam suggests spacetime itself might have a similar structure at its heart. In this foam, the very notions of before and after, of here and there, break down. Causality and continuity dissolve into a probabilistic haze. Tiny wormholes might spontaneously thread through the foam, connecting disparate points only to pinch off and vanish. This is the ultimate rebellion against the classical stage. Einstein's beautifully curved continuum is an average, a large-scale illusion that emerges from unimaginably fine-grained, random turbulence. We are walking on what seems like solid ground, but beneath our feet, at distances a billion times smaller than an atom, the floor of the universe is a boiling sea of maybe. This fundamental incompatibility is the single greatest crisis in modern physics. On one hand, we have general relativity, a masterpiece of geometry that describes the cosmos with breathtaking elegance. On the other, we have quantum mechanics, an astonishingly accurate rulebook for the subatomic world. Both are proven correct within their own domains, yet they speak completely different mathematical languages and describe reality in mutually exclusive ways. General relativity says spacetime is a smooth, deterministic fabric. Quantum mechanics says that at its foundation, everything is probabilistic and fuzzy. When we try to combine the equations to see gravity through a quantum lens, the math breaks down into nonsense, spitting out infinities that cannot be reconciled. One major reason for this schism is gravity's profound weakness. At the scale of an atom, the gravitational pull between two particles is about 40 orders of magnitude weaker than the electromagnetic force holding them together. It is like comparing the pull of a single proton to the force of the entire planet Earth. This incredible feebleness makes the quantum effects of gravity nearly impossible to detect in a lab, leaving us with a theory that works perfectly for planets and galaxies, but has no voice in the chaotic choir of the quantum realm. Yet we know these two worlds must collide. There are places in the universe where enormous mass is compressed into a vanishingly small volume, where the vast domain of gravity meets the tiny domain of quantum rules. The center of a black hole is one such place, a singularity where density becomes infinite and spacetime curvature so extreme that general relativity alone cannot describe it. Similarly, if we rewind the cosmic clock to the first fleeting moments of the Big Bang, the entire observable universe was smaller than a single atom. At that scale, the quantum fluctuations of spacetime itself would have dictated the fate of everything to come. To understand these ultimate origins and boundaries, we cannot have two separate rulebooks. We need a single, unified framework that seamlessly blends the very large and the very small. This is the quest for a theory of quantum gravity, and by extension, a theory of everything. It is a search not just for new particles or forces, but for a deeper language that can describe the fundamental substance of reality, revealing what space and time truly are when the curtain of our perception is pulled all the way back. The search for a single rulebook has led physicists down a path of breathtaking imagination. One of the most prominent candidates is string theory, a vision where the fundamental building blocks of reality are not point-like dots, but inconceivably tiny, vibrating loops or strands of energy. These are the strings. In this radical picture, an electron is not a featureless speck. It is a string vibrating at one specific frequency, like a single note played on a microscopic violin string. A quark is that same string vibrating at a different frequency. A photon, the particle of light, is yet another distinct vibration. Every particle in the universe, every force carrier, is just a different resonant pattern on these fundamental strings. The symphony of these vibrations composes all of matter and energy. This elegant idea holds immense promise because one type of vibration on the string corresponds perfectly to the properties we expect from the graviton, the hypothetical quantum particle of gravity. For the first time, gravity is not forced into the quantum world. It emerges naturally from the same music as everything else, but this beautiful harmony comes at a strange cost. The mathematics of string theory only works if the universe has more than the three spatial dimensions we experience. To avoid chaotic inconsistencies, the equations demand extra dimensions of space, often 10 or 11 total. Where are these hidden dimensions? The theory proposes they are curled up or compactified at a scale so small we could never perceive them directly. Imagine a long, thin garden hose. From a great distance, it looks like a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto its surface, you would discover it has a second dimension, curled into a tiny circle around its circumference. Our universe might be similar. At every point in the three-dimensional space we see, there could be 6 or 7 extra spatial dimensions, curled into a complex microscopic shape called a Calabi-Yau manifold. These dimensions are not places you could travel to. They are part of the fundamental geometry of reality at the Planck scale, and their specific shape determines the properties of the particles and forces we observe, much like the shape of a violin's body determines the sound it can produce. String theory, in its most ambitious form, suggests that spacetime itself is not a fundamental stage. It is an emergent phenomenon, a consequence of the collective behavior of these vibrating strings and the way their hidden dimensions are woven together. The smooth fabric of general relativity would be a kind of illusion, a large-scale average of an unimaginably intricate, multi-dimensional quantum tapestry. Yet this grand vision remains, for now, a magnificent mathematical edifice without direct experimental proof, a symphony waiting for its first note to be heard in our world. String theory is not the only contender in the quest for a quantum universe. A radically different approach, born from a different mathematical lineage, asks a more direct question. What if we apply the rules of quantum mechanics not just to matter, but to the very fabric of spacetime itself? This is the promise of loop quantum gravity. It does not add extra dimensions or vibrating strings. Instead, it takes Einstein's geometric picture of general relativity and subjects it to the process of quantization. The result is a universe where space and time are not smooth and continuous but grainy. They are made of discrete, indivisible pieces, the smallest possible units of area and volume. In this view, there is a true atom of space. Imagine the fabric of spacetime not as a silken sheet, but as a vast, intricate network. The threads of this network are tiny, one-dimensional loops of gravitational field woven together at their intersections. These loops are the fundamental quanta, the pixels that make up the cosmic picture. Where they link together, they create a node, and the entire network of nodes and links forms the geometry of the universe. This spin network, as it is called, is not embedded in space. It is space. The smooth, three-dimensional expanse we move through emerges from the collective connections of trillions upon trillions of these quantum links, much like a smooth piece of cloth emerges from a weave of individual threads. This discreteness solves a major problem of singularities. In Einstein's theory, at the heart of a black hole or at the beginning of the Big Bang, the curvature of spacetime becomes infinite. The equations blow up. But if space itself is made of finite, quantized pieces, you cannot compress it to a point of zero volume. There is a smallest possible size. This leads to loop quantum gravity's most profound cosmological prediction. If we run the cosmic film backward to the hot, dense beginning, we do not reach a singularity of infinite density. Instead, as the universe contracts, the quantum nature of spacetime resists further collapse. The gravitational force described by these woven loops becomes repulsive at extreme densities. The contraction stops and the universe bounces, expanding outward once more. This is the big bounce. Our universe may not have been born from a singular point where physics breaks down. It could be one cycle in an endless cosmic rhythm, a phoenix arising from the ashes of a previous cosmos. Here, the arrow of time might reverse during the contraction phase, or simply continue through the bounce, offering a vision of eternity where beginnings are merely transformations. While still a theoretical framework without direct experimental confirmation, loop quantum gravity provides a powerful alternative narrative. It suggests that spacetime is not a stage but a tapestry, and that the universe itself may be an eternal, breathing entity woven from the smallest possible stitches of reality. The tapestry of spacetime may be woven from threads we cannot see, but could the entire picture be nothing more than a projection? This is the startling claim of the holographic principle, an idea so radical it suggests our three-dimensional universe with all its depth and richness might be a cosmic illusion. To understand this, we must return to the enigmatic surface of a black hole. In the 1970s, physicist Jacob Bekenstein made a revolutionary proposal. He argued that a black hole's event horizon must have entropy, a measure of its hidden information content. This was shocking because entropy is a property of disorder, and black holes were thought to be the simplest objects in the universe, described only by their mass, spin, and charge. Stephen Hawking later showed that black holes aren't completely black. They emit a faint thermal radiation, now called Hawking radiation, and have a temperature. This forged a deep link between gravity, thermodynamics, and quantum mechanics, black hole thermodynamics. The key insight was that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. All the information about everything that ever fell into the black hole is somehow encoded on its two-dimensional boundary surface. It is as if the entire three-dimensional interior is described by a theory living on its two-dimensional skin. This is the seed of the holographic principle. It proposes that all the information contained within any volume of space can be fully described by a theory that exists on the boundary enclosing that volume. Think of a credit card hologram. The flat, shiny sticker holds no depth, yet when light hits it, it projects a stunning three-dimensional image that seems to float in space. The holographic principle suggests our universe might work the same way. The stars, planets, and even you, in all your apparent three-dimensional solidity, could be a magnificent projection from a vast, distant, two-dimensional surface where information is stored like pixels on a cosmic film. This flips our intuition about reality on its head. We think the most real things are the objects around us occupying volume, but this principle implies that the true, fundamental description of the universe might require one less dimension. The richness of our 3D experience, the feeling of moving through space, the solidity of matter, could be an emergent phenomenon, a kind of shadow play cast from a simpler, flatter reality. The implications are dizzying. If true, it means the universe has a finite amount of information, a maximum number of bits it can contain, set by the area of its boundary, not its volume. It blurs the line between what is real and what is encoded data, suggesting that at the most fundamental level, the cosmos might be a vast information processing system, and space-time itself is its output. We are left to wonder if our reality is a hologram, what or who is holding the projector. The holographic universe is a projection, but could we ever step through the screen? The equations of general relativity, in their raw mathematical form, allow for a structure so strange it feels lifted from fantasy, a wormhole, often called an Einstein-Rosen bridge. This is not a tunnel dug through space, but a shortcut in the folded geometry of spacetime itself. Picture the universe not as a flat sheet, but as a crumpled piece of paper. Two distant points on that sheet could be brought close together if you fold the paper, and a wormhole would be a pencil stab connecting them, creating a bridge through the higher dimension. In theory, such a structure could connect two places billions of light years apart, or even two different moments in time, offering a passage not just through space but through history. The mathematics does not forbid it, but building one is another story entirely. A natural wormhole, if it could form, would be catastrophically unstable. The moment you tried to pass through, the immense gravitational forces would snap the bridge shut like a rubber band, crushing anything inside. To hold it open, to make it traversable, the equations demand something truly bizarre: exotic matter. This is not antimatter or dark matter. Exotic matter would need to possess negative energy density, creating a kind of anti-gravity that pushes the walls of the wormhole apart, resisting the natural urge to collapse. While tiny quantum effects can produce fleeting amounts of negative energy, the quantities needed to stabilize a human-sized wormhole are astronomical and far beyond any technology we can conceive. So while wormholes are a beautiful feature of Einstein's geometry, they remain firmly in the realm of mathematical possibility, not engineering. If a stable wormhole could link different times, it would invite the most famous conundrum of time travel, the grandfather paradox. Imagine you step through a wormhole into the past and prevent your own grandfather from meeting your grandmother. If you are never born, how could you have traveled back to change the past in the first place? This logical contradiction seems to make consistent time travel to the past impossible. Physics offers a few speculative ways out. One is the Novikov self-consistency principle, proposed by Russian physicist Igor Novikov. It asserts that the laws of physics simply will not allow paradoxes to happen. If time travel to the past is possible, then any actions you take there were always part of history. You might intend to change the past, but every choice you make, every interaction you have, will inevitably conspire to produce the exact present you left from. You could not kill your grandfather because in the consistent timeline you simply did not. The past is immutable, not because it is recorded, but because any attempt to alter it is woven into its fabric from the beginning. Your journey back was always an event that occurred, and your presence there causes no ripples that were not already there. Another possibility, favored by some interpretations of quantum mechanics, is the many worlds hypothesis. In this view, every quantum decision spawns a new, branching universe. If you travel to the past and alter an event, you are not changing your own history. You are simply stepping onto a new branch of the multiverse, creating an alternate timeline where your actions have consequences, but your original timeline remains untouched and paradox-free. These are not answers, but frameworks for thinking about the profound constraints reality might impose. They highlight a crucial distinction. The laws of physics, as we currently understand them, do not explicitly ban time travel in theory. But they surround it with such immense physical barriers and logical safeguards that it remains, for all practical purposes, a closed door. Wormholes and time machines are less like blueprints and more like philosophical tools, stressing our theories to their breaking point to see what truths might spill out. The paradoxes of time travel force us to confront the most basic mystery of all. Is time itself real? We feel its flow with every heartbeat, every fading memory, yet physics offers no equation for now. In the block universe of relativity, the question is turned on its head. Past, present, and future are all equally real, fixed locations in the four-dimensional loaf. Your birth, your reading of this sentence, and every moment to come already exist as permanent coordinates in spacetime. In this view, the flow of time is an illusion of consciousness, a mental trick as we slide along our world line from one slice of the block to the next. The future is not waiting to be written, it is simply a place you have not yet visited. This is the eternalist perspective, and it emerges directly from Einstein's equations where there is no privileged present. But this feels deeply alien to our lived experience. The opposing view, called presentism, insists that only the current moment is real. The past is gone, a set of memories and records. The future is pure potential, not yet actualized. In this familiar picture, the universe is a single, razor-thin slice of now that is constantly updating, moving into the unwritten future and leaving a fixed past behind. Relativity seems to shatter this idea, as there is no universal clock to define which now is the true one across separated points in space. Yet the feeling persists, a stubborn ghost in the machine of physics. Some theorists searching for quantum gravity propose a third, even more radical possibility. Physicist Carlo Rovelli suggests that time, as a fundamental, smooth flow, may not exist at all in the basic description of nature. At the quantum level, where the spin network of loop quantum gravity operates, there may be no variable for time. Instead, what we experience as the passage of time could be an emergent property, a statistical result of countless quantum interactions. It would be like the sensation of temperature. A single molecule does not have a temperature. Temperature is a collective property of trillions of molecules jostling together. Similarly, time may be what emerges when we zoom out from the frenzied quantum relations between events. In this view, the arrow of time is tied to the growth of quantum correlations and entanglement. The universe starts in a low-entropy, relatively simple quantum state. As systems interact and become entangled, the web of correlations grows more complex, creating an irreversible direction that our brains interpret as the flow from past to future. So is time real? The answer depends on the scale. As a fundamental ingredient of a final theory, it may vanish. As a large-scale, emergent phenomenon governing our classical world and our consciousness, it is overwhelmingly real in its consequences. We are caught in the middle, beings built by entropy, perceiving a flow that the universe's deepest laws might not contain. This leaves us with one final, humbling frontier. If time is not fundamental and space is a tapestry of quantum threads, then what are we, the observers who perceive this magnificent illusion? The most abstract ideas must eventually face the cold, hard light of evidence. Our journey through the quantum foam and holographic projections is not pure philosophy. It is a scientific quest, and that means building machines to listen for whispers from the edge of reality. We are now in an era of extraordinary experiments designed to test the very fabric of spacetime. The first direct confirmation that this fabric can ripple came in September 2015, when the Laser Interferometer Gravitational Wave Observatory, or LIGO, detected a tremor from a collision over 1 billion light-years away. Two black holes, each dozens of times more massive than our Sun, spiraled into each other and merged. Their violent dance sent gravitational waves, literal ripples in the curvature of spacetime, propagating outward at the speed of light. By the time they reached Earth, these waves had stretched and squeezed the 4-kilometer long arms of LIGO detectors by a distance 10,000 times smaller than a proton. That infinitesimal shudder was captured, proving that spacetime is not just a static stage, but a dynamic medium that can vibrate like a drumhead. Collaborating observatories like Virgo in Italy and Kagra in Japan now form a global network, listening for the cosmic crashes of neutron stars and black holes, turning gravity itself into a new sense for exploring the universe. While LIGO listens to the catastrophic warps of the present, other instruments peer back toward the first tremors of time. The James Webb Space Telescope is not just capturing stunning images of nebulae. It is a time machine collecting light that has traveled for over 13 billion years from the earliest galaxies that coalesced after the Big Bang. By studying the formation and distribution of these ancient structures, cosmologists can test the predictions of inflation, the theory that the universe underwent a period of hyper-fast expansion in its first fraction of a second. The specific patterns imprinted on the cosmic microwave background and the large-scale web of galaxies act as a fossil record, constraining our models of how spacetime itself unfolded in its infancy. Did it expand smoothly, or were there quantum fluctuations in the gravitational field, as some theories of quantum gravity predict? The data flowing from these telescopes provides the concrete clues to answer these questions. Perhaps the most tantalizing experiments are those that bring the search for quantum gravity down to Earth, to tabletop scales. Scientists are designing exquisitely sensitive experiments to probe the nature of gravity at distances smaller than a millimeter. Could Newton's law of gravity, which works perfectly for planets and apples, break down at the scale of a human hair? Some theories, like those involving extra dimensions, predict that gravity could become stronger at microscopic ranges. By measuring the gravitational attraction between precisely crafted, oscillating masses in a vacuum chamber, researchers hope to see a deviation, a hint of new physics. Other experiments look for indirect signatures of quantum spacetime. One approach involves using supercold, superconducting circuits to create artificial atoms that interact with microwave photons. By studying how these quantum systems decohere, lose their quantum properties, scientists might detect a fundamental graininess in spacetime, a faint buzz from the quantum foam that disrupts the pristine quantum states. It is a hunt for the universe's pixelation. These are the three frontiers of testing, listening to the echoes of colossal collisions, reading the ancient light from creation's dawn, and sensing the faintest tremors in a lab. The theories of strings, loops, and holograms provide the breathtaking maps, but it is the painstaking, incremental work of experiment that will tell us which map, if any, corresponds to the true territory of reality. Science at this frontier is a conversation between the wildest imagination and the most disciplined observation, a dialogue aimed at one goal: to hear what the universe is saying about its own deepest nature. These revelations about the cosmos are not just about distant stars or abstract equations. They are a mirror held up to our own existence. If space-time is not a fixed stage but an emergent, relational phenomenon, then our perception of reality is not a transparent window. It is a highly specific interface shaped by the scale of our bodies and the limitations of our senses. We experience a smooth, three-dimensional world flowing in one direction because that is what emerges from the quantum chaos at our level of reality, just as the solidity of a table emerges from the empty space between buzzing atoms. Our entire conscious experience, the feeling of being here now, in a tangible place, is a brilliant, useful illusion generated by a brain evolved to navigate a middle world, not to perceive its fundamental code. This means that asking what space and time are is inseparable from asking what we are as observers within them. We are not passive spectators on a pre-built set. We are active participants whose very perception helps define the classical reality we see from the quantum fog. Our quest to understand the universe's birth and its ultimate fate is therefore a quest of self-understanding. We are the universe becoming conscious of itself, using the tools of physics to trace our own lineage back to the first moment when space and time began to mean something. This journey backward inevitably pushes our theories to their limits, and in doing so, they often suggest possibilities that stagger the imagination. The leading theory of the universe's first instant cosmic inflation proposes a period of hyper-fast expansion that smoothed and stretched the infant cosmos. But the mathematics of inflation does not naturally stop everywhere at once. It suggests a breathtaking possibility: our entire observable universe, with its hundreds of billions of galaxies, may be just one bubble in a frothing, eternal multiverse. In this picture, the rapid stretching of space-time could be happening forever in a broader cosmic landscape, with new bubble universes constantly nucleating, each with its own random set of physical laws and constants. Some might have stronger gravity, rendering stars impossible. Others might have no matter as we know it. Our universe is not special or fine-tuned in this vast ensemble. It is simply one where the numbers allowed atoms, planets, and life to form. We can never see beyond our own bubble's horizon, as the space between us and other bubbles expands faster than light can cross it. This makes the multiverse a profound philosophical proposition more than a testable scientific one, yet it emerges directly from our best attempts to model the physics of primordial spacetime. It forces us to confront the humbling scale of existence. Our entire history, from the Big Bang to this very moment, might be a local story in an infinite, eternal metacosmos where the concepts of beginning and end lose their meaning. Ultimately, the mystery of space and time is the mystery of existence itself. Every question leads to a deeper, more fundamental puzzle. We have peeled back layer after layer, from Newton's absolute stage to Einstein's dynamic fabric, from quantum foam to cosmic holograms. With each revelation, the universe has become more strange, more beautiful, and more deeply interconnected. The search is far from over. The next great theory of quantum gravity waits to be discovered, promising to rewrite our story once more. But this endless pursuit is not a path to despair. It is a celebration of the human spirit's capacity for wonder. We are finite creatures, bound to a speck of dust in a forgotten corner of one galaxy, armed only with mathematics and curiosity. Yet we have managed to decode the life cycles of stars, feel the ripples of black hole collisions, and peer back to the dawn of time. We may never find a final, complete answer to what space and time actually are. But in the asking, we discover something equally profound. our own place as storytellers in a cosmos vast enough to contain every possibility and mysterious enough to keep us dreaming forever. We have traveled from a solid Earth beneath crystal spheres to a universe woven from probabilities. Our understanding of space and time has been shattered and remade not once but again and again. We began with a static stage, an absolute backdrop where events played out. We saw that stage vanish, replaced by a flexible fabric where motion warps time and shrinks space. We watched that fabric become curved by mass, bending light and stretching seconds. We peered into its quantum heart, where it dissolves into a foaming sea of potential. We considered the possibility that this entire rich, three-dimensional reality might be a holographic projection from a distant, two-dimensional surface. This is not a story about things in the universe. It is the story of the universe itself. Space and time are not a container we inhabit. They are the dynamic, interactive substance from which everything, stars, planets, and our own conscious minds emerges. They are the canvas and the paint, the stage and the performance all at once. We are not merely spectators on this stage. We are part of its unfolding narrative, a pattern in the tapestry, momentarily aware of the weave. The greatest mystery, then, is not some distant galaxy or hidden dimension. It is the very ground beneath your feet and the moment you are living through. The stage upon which you stand is the deepest enigma of all. What do you think lies at the heart of this mystery? Share your most mind-bending thoughts on space and time in the comments below, and subscribe to join us as we continue exploring the profound wonders of our cosmos.